Welcome to the fifth lecture of microwave engineering. The lecture is about lossless transmission line and voltage standing wave ratio. So before this lecture, in lecture number 4, we have seen the different parameter, like we have seen the characteristic impedance of a line, which is the ratio of R plus j omega L divided by G plus j omega C. Then we have derived the voltage and current equation based on this parameter, that is based on reflection coefficient, and then we are having a relation, that is the reflection coefficient is equal to ZL minus Z0 divided by ZL plus Z0, and from that we have some conclusion defining the from the definition of VSWR, that is definition of reflection coefficient, that is ratio of reflected voltage divided by incident voltage. Now we will see the lossless transmission line. So as the name suggests, the lossless transmission line is the line which will have a very, or you can say it does not have any loss. So name itself suggests that there will be no loss. Now when we have seen the transmission line, the model of a transmission line, we have defined some distributed parameter. We have taken a very small element of a very small length of a transmission line, delta x, and we have defined the element R delta x, L delta x, C delta x and G delta x. So when we have defined, I have told that this resistance account for all the losses in the transmission line, while this G will account for, because these are two conductor, whatever the leakage current will be, it will be through this G. So this R and G will account for all the losses in a transmission line. So if somehow will reduce or will make this equal to 0, then our line will be lossless transmission line. So for this we are having condition like if this R or G should be very smaller than this component L and C, then we will have either a low loss or very you can say lossless or very low loss transmission line. So we will see. So the condition for the low loss, or you can say lossless line, is when R is equal to 0 and when G is equal to 0. When both this loss parameter will be equal to 0, then line is called lossless transmission line. Lossless transmission line. Now we know the equation of, let us first take the equation of characteristic impedance. So characteristic impedance we have defined, that is the ratio of under root of R plus j omega L divided by G plus j omega C. Now for the lossless line, as the condition suggests, R is equal to G is equal to 0, so we will have only under root j omega L divided by under root j omega C. It means this will be equal to under root L by C. So the characteristic impedance will only depend upon under root L by C. The next parameter is the propagation constant. We have defined propagation constant, that will be under root of R plus j omega L into G plus j omega L. So R plus j omega L into G plus j omega L. Now R and G are equal to 0 for the lossless transmission line. So we are having R is equal to 0, we are having G is equal to 0, so only thing will be under root j omega L multiplied by under root j omega C. So this will turn as a j omega will be out of the bracket and we will have under root L into C. Now we have done one more thing while defining this propagation constant. That was, we have defined the propagation constant is equal to alpha plus j beta. So we have told at the time of definition of this propagation constant that it is in general a complex quantity which will have a real part as well as the imaginary part. Now after substituting the lossless condition, we got the reflection coefficient is equal to j omega under root LC. So it shows that for a lossless line it will have only imaginary component, it does not have any real component. So for lossless transmission line, the alpha is equal to 0. If alpha is equal to 0, it means alpha is attenuation constant, which display how much attenuation is there in a transmission line per meter. So if alpha is equal to 0, it means it does not have any attenuation. No attenution means it does not have any losses. So alpha is equal to 0. Now the phase J is the imaginary component is JB, where B is called phase shift constant. So the line, whatever we will have, this lossless line, it will have only imaginary component. So only phase component is there. So everywhere whenever there will be lossless line, we will have the gamma or the propagation constant is equal to j omega under root LC. So prior to this, wherever we have the voltage and current equation where we will have a gamma, then we will replace that gamma for the, now we will do all the analysis for the lossless line in next some lecture. So what we will do is we will replace this gamma with this j omega under root LC, or simply will will replace with only JB, because alpha is constant, so gamma is only equal to JB. So if we compare this to JB is equal to j omega under root LC, then we will get beta is equal to omega under root LC. So it will have only beta component, phase shift component, while alpha component will be equal to 0. So moving ahead, we will have now voltage and current equation as we have seen in earlier lecture. That is, the voltage is given by VL is equal to V plus, now instead of e raised to gamma L, earlier we will have e raised to plus gamma L, but now we will substitute gamma is equal to alpha plus j beta, and alpha is equal to 0 for lossless line, so it will be e raised to JBL. Earlier it was e raised to gamma L. Instead of gamma, we have substituted alpha plus JBL. Now alpha is equal to 0, so naturally it will be V plus e raised to JBL, and V minus e raised to minus JBL. So this is for voltage, and for current we will have IL is equal to V plus by Z0 e raised to JBL minus V minus divided by Z0 e raised to minus JBL. So this is for current. So this shows the voltage at any point in the transmission line is summation of these two waves, that is forward traveling wave and reflected wave, while the current is also in terms of voltage, and so this will also represent the forward traveling wave, and this will be reverse traveling wave. So the algebraic summation of the component will be there. Now we have defined earlier the reflection coefficient at any point on line is, it will be ratio of reflected voltage divided by incident voltage e raised to minus 2 gamma. This is the definition of reflection coefficient. This we have defined in earlier lecture. Now once again, if we will take only the lossless line, then it will be V minus divided by V plus e raised to minus 2. Instead of this gamma, we will have alpha plus j2 beta, alpha plus j beta. So alpha is equal to 0, so it will be it will be e raised to jb. So it will be e raised to minus 2 jb, j beta. So this will be the reflection coefficient for the lossless transmission line, and this is the voltage and current relation for the lossless transmission line. One more thing, while we have defined this reflection coefficient, so reflection coefficient At the load end we have told that when L is equal to 0, when we have taken the reference as a load end, then L is equal to 0 will be equal to load end, and we have this voltage, this reflection coefficient is equal to V minus divided by V plus. In general, this reflection coefficient is a complex term. Reflection coefficient is a complex term. It means it will have a real part as well as imaginary part. So we'll write in general the reflection coefficient at any point on line will have, this will be V minus by V plus is equal to reflection coefficient at load, and this will be minus 2 J beta. Okay. So we'll write this as a reflection coefficient at any point on line is reflection coefficient at load into e raised to minus J2 BL. Sorry, there will be L everywhere. Now once we define this, we'll substitute this reflection. We already got this equation of voltage and current in last lecture in terms of a reflection coefficient. So we'll simply write this reflection coefficient, voltage and current in terms of a reflection coefficient. So we have VL is equal to V plus e raised to JBL 1 plus reflection coefficient at any point on line, while in terms of a current at any point on line is V plus by Z0 e raised to, sorry, there will be e raised to, okay, e raised to JBL 1 minus reflection coefficient at any point on a line. This can be further modified as V plus e raised to JBL, instead of this complete reflection coefficient at any point on line, we'll write this in terms of a reflection coefficient at load and multiply by e raised to minus J2 beta L. Similarly, we can write the current, that will be V plus by Z0 e raised to JBL 1 minus reflection coefficient at load multiply by e raised to J2 beta L. So we got this equations in terms of a voltage and reflection coefficient. Once we got this component, there is one more thing we have just discussed, that is the reflection coefficient is in general a complex term. Let us take the reflection coefficient is equal to, it will have some magnitude component and it will have some phase component, because it is a complex quantity. So the magnitude of reflection coefficient will define as a, this will represent a magnitude of reflection coefficient, and the phase term will be denoted by phi. So the phase of the reflection coefficient will be equal to e raised to j phi. Now defining this, now we'll substitute this into this equation of voltage and current. So for this, substituting this in these two equation, we'll write this will be, voltage will be V plus e raised to JBL 1 plus reflection coefficient at load, or simply this will be the magnitude of reflection coefficient at load into e raised to, now we have substituted this reflection coefficient is equal to magnitude into phase of reflection coefficient. So this will be 1 plus reflection coefficient e raised to minus j will be common, so it will be j phi minus 2 beta L, and for current it will be, for current at any point on line it will be, so this will be V plus by Z0 into e raised to j beta L. Now it will be 1 minus magnitude of reflection coefficient multiplied by e raised to j pi minus 2 beta. So we got the relation of voltage and current in terms of the complex reflection coefficient. Now it can be seen that at each and every point this quantity, that is e raised to j phi 2bl, this represent, let us take this as a e raised to j phi minus 2bl. So what this quantity represent? This is this L represent the length and this represent beta represent phi. So each and everywhere this complete will represent phase, that is phi minus 2bl will represent a phase. So as one moves along the transmission line, the length L, therefore this phase changes. So if we'll change this L, if we'll move from one end to, this is our load end, so if one moves from one end to other end of a transmission line, this phase quantity will change, because this will be a, let us take, this will be a constant one, so this quantity will change. It means it is, this is changing at each and every point on a transmission line. So this is nothing but our reflection coefficient changes at each and every location on a transmission line. So now the question is, at some location where this beta L, beta is what, 2 pi by lambda, beta is 2 pi by lambda, and this length is also in terms of L. So at some point in a transmission line, at the location where this phi minus 2 beta L, this our phase component phi minus 2 beta L, that will equal to pi. So what will happen? E raised to, it will be e raised to j pi. So e raised to j pi will be equal to plus or minus 1. So e raised to j phi minus 2bl will be equal to plus or minus 1. So when it will become plus or minus 1, then from this voltage and current equation, let's say the when okay, let us take when this e raised to phi 2bl become 1. So e raised to this e raised to j theta j phi e raised to j phi minus 2bl. If this quantity become plus 1, then what will happen? So in voltage at any point on line, what will happen? It will be, this quantity will be 1, so this will be equal to 1. So the voltage term will add up, so it will be V plus 1 plus magnitude of reflection coefficient. We will have a addition of this, it means we will have a maximum voltage, we will have a voltage maxima. But in current, what will happen? When this will be equal to 1, this will be, this is 1, so the current will be V plus divided by Z0 1 minus reflection coefficient. So this will become negative, not a negative, it will become minimum. So this will be high minimum. So whenever e raised to j 2bl become plus 1, the voltage term will add, while in current there will be subtraction. So we will get a current minima and voltage maxima. Similarly, when this quantity is equal to minus 1, then what will happen? Then voltage will, it will be subtraction of voltage. So this will be V plus 1 minus reflection coefficient. So this will be our V mean, and for current we'll have IL is equal to V plus divided by Z0 1 plus reflection coefficient, because now this will be a negative one, so we are having a addition. So what we are seeing is, on a transmission line, when voltage is maximum, current is minimum, and when current is maximum, voltage is minimum. So when we draw a voltage and current waveform on a transmission line, let's say this is our load end and this is the voltage. Let us take, this will be, let me draw a good picture. So when we are having a, let us take, this is the voltage on a transmission line. Now this voltage, whenever there will be voltage maxima, then current will be minimum, and whenever there will be current minimum, voltage will be maximum. Let us take, this is our current, okay, and will have its, whenever current is maximum, voltage is minimum, and whenever voltage is minimum, current is, so this is our voltage and this is our current. So whenever voltage is maximum, so this is V max and this is I mean, current will be minimum, while whenever there will be voltage minimum, current will be maximum. And the magnitude of minimum and maximum voltage and current we have seen, this will be equal to, so V max is equal to V plus 1 plus gamma L, 1 plus reflection coefficient, and at that time I mean is this. Now at this point we'll define one more quantity, and that is called as voltage standing wave ratio. This will be voltage standing wave ratio. What is this? According to its name, this is the ratio of voltage, where in this standing wave pattern. So where standing wave pattern will form? Whenever there will be mismatch in a load. Whenever there will be mismatch in a load, there will be a reflected voltage and there will be a forward voltage. The reflected and forward voltage will always add and it will form a standing wave. So in a standing wave, there will be now maxima and minima. So maxima, if we will talk in terms of a voltage, the ratio of maximum voltage divided by minimum voltage is called voltage standing wave ratio. So according to definition, it is ratio of V max divided by V mean. It is ratio of maximum voltage divided by minimum voltage in a transmission line in a standing wave is called voltage standing wave ratio. Now according to definition, so we'll substitute this V max. V max is equal to V plus 1 plus magnitude of reflection coefficient, and V mean is V plus 1 minus magnitude of reflection coefficient. So so this will be 1 plus reflection coefficient. So we'll denote this by S. So S, that will be equal to VSWR, that is voltage standing wave ratio, equal to 1 plus reflection coefficient divided by 1 plus magnitude of reflection coefficient divided by 1 minus magnitude of reflection coefficient. This is called as standing wave ratio. Now we'll see, now what is the physical interpretation of this voltage standing wave ratio. So voltage standing wave ratio will denote is an accurate indicator of the reflection in a transmission line. So by definition Vmax is greater than Vmin. This is ratio of Vmax by Vmin. So Vmin is always less than Vmax. So the reflection coefficient is always greater than 1. It is from 1 to, if it will be equal to, if we know the, we know reflection coefficient is always, reflection coefficient is between 0 to 1. 0 corresponds to perfect match, while 1 corresponds to worst case condition or no match or no power transfer. So if we'll substitute the value of reflection coefficient, then the reflection coefficient will denote, now this voltage standing wave ratio is 1 plus reflection coefficient divided by 1 minus reflection coefficient. So when we substitute this reflection coefficient in a transmission line, then let us take, once again we will take 3 cases. We have ZL is equal to Z0 corresponds to reflection coefficient is equal to 0. Then we will have ZL is equal to 0, which is short circuited transmission line. We will have ZL is equal to, this reflection coefficient is equal to 1. We will have ZL equal to infinity, and that time we have this equal to 1. So once again we will do same analysis for voltage standing wave ratio. So this voltage standing wave ratio, let us take this for a perfect match. When the magnitude of reflection coefficient is equal to 0, this is, let me write, this will be perfect match. This is short circuited and this is open. So these two represent worst case. So for perfect match, that is ZL is equal to Z0, this reflection coefficient is equal to 0. We'll substitute this in this definition. So we'll get the VSWR is equal to 1 divided by 1. So that will be equal to 1. While for short circuit condition, we'll have short circuit and open circuit condition, we'll have this equal to, so rho L or simply reflection coefficient is equal to 0, as reflection coefficient is equal to 1. When it substitute this in a VSWR equation, then it will be 1 plus 1 divided by 1 minus 1. So 1 plus 1 divided by 1 minus 1, this will be 1 upon 0. It means for this we will have VSWR is equal to infinity. So the value of reflection coefficient, this VSWR is from always from 1 to infinity, where this 1 corresponds to reflection coefficient 1, reflection coefficient 0. It means perfect match. We can also see from this, that is Vmax divided by Vmin. Vmax by Vmin, Vmax is always greater than Vmin, so S is always greater than, it will be always greater than 1. So when S is equal to 1, it means there will be a perfect match. There will be ZL is equal to Z0, there will be perfect match and all the power will be delivered to the load and nothing is reflected back. While in case of reflection, magnitude of reflection coefficient is equal to 1, we'll have two conditions, either short circuited transmission line or a open circuited transmission line. Then for this condition we'll have a reflection coefficient is equal to infinity. Sorry, we have a VSWR, voltage standing wave ratio, is equal to infinity. So 1 corresponds to perfect match, while the infinity corresponds to worst case. We don't want this anytime. We always want reflection coefficient between 1 to 2. In any component or in any microwave circuit, the reflection coefficient must be between 1 and 2. So it represents a good match in a component or a good match in a microwave circuitry. So in this lecture we have seen the voltage standing wave ratio and we have seen the lossless transmission line. We'll see the more elaboration in transmission line in next lecture. If you have any query, you can write to me in my email ID, that is Balwant Makwana, BALVANT Makwana, MAKWANA @gecrajkot.ac.in, rajkot.ac.in. Thank you very much.